Hello everyone and welcome to the third live session of the first International Electronic Conference on Actuator Technology, Materials, Devices and Applications. This conference has been organized by MDPI and the Actuators Journal, and it is chaired by Professor José Luis Sánchez Rojas from the University of Castilla-La Mancha in Spain and by Professor Tatiana Minaf from Tampere University in Finland. I would like to thank our chairs and conference committee for making this conference possible and for all the participants for joining us today. Until this Friday, November the 27th, you can read and comment all the papers presented to the conference. So they are now available at the conference website, so check the website. Our session today is on actuator materials, and our session chair is Professor Kenji Uchino from Penn State University in the States. Professor Uchino will both introduce and wrap up the session, and we will have 3 other keynote lectures today. Professor Clive Randall from Penn State University in the States, Professor Isaku Kanno from Kobe University in Japan, Professor Jongho from Yunnan University in Korea. After each speaker presentation, we will hold a Q&A session during which we will address the questions submitted by live online audience. So please, if you're joining us live, type your question at any time during the session in the Q&A box. I would also like to remind everyone that this webinar is being recorded and that we will post the recording in the conference website. Now I'd like to introduce our session chair. Dr. Kenji Uchino is a well-known pioneer of piezoelectric actuators. This terminology was created in the 1970s when he started this field. He has been a university professor for 45 years, a company president and vice president for 21 years, and a government officer for 7 years, including the US Navy ambassador to Japan. He's currently professor of electrical engineering, material science, and engineering, and director of International Center for Actuators and Transducers at the Pennsylvania State University. Now, Professor Uchino, the floor is yours, and everyone enjoy the webinar.
Happy Thanksgiving. It's the holiday in the United States. Good morning, early morning here. Anyhow, thank you very much for attending the first International Electronic Conference of Actuator Technologies, Materials, Devices, and Application Areas. Today, I will organize the Piezoelectric Actuator Materials, and this will be held from 8:30 till the 10:30, okay? First of all, I would like to introduce myself. I have been a university professor for 45 years, 18 years in Japan, and already close to 30 years at Penn State Universities. Company executive, president, vice president for 21 years, operating 5 small business industries, and government officer for 7 years. As Elena already introduced, the most recent is a US Navy ambassador to Japan, to negotiate with the rescue program after the big earthquake hit in Japan. And I'm well known as a discoverer of piezoelectric actuators and relaxer single crystals. And actually, I'm an inventor of the multi-layer actuator structures and magnetoelectric composite structure and so on. And I'm teaching engineering department as well as the business school. And also I started to work for the law school. So personally, I'm a Buddhist, Zen practitioner, as you can see here. And also personally, one of my eldest grandson is already in the university. It's time for my retirement, I'm thinking. So today's lecture, they already introduced Clive, Isaku, and Jongho, and myself will present on the low temperature sintering and thin film PZT MEMS, and also aerosol deposition thin film. These 3 are basically the preparation technique. And the final is also materials development, but high power the heat generation. So now I would like to pass to the Clive Randall, Professor Clive Randall, for his presentation. I will stop here.
Thank you, Kenji. Welcome, everybody. Thank you very much to the organizers. Thank you very much, Elena, for getting us organized this morning. And also thank you for my co-presenters for really an interesting session, which has got a lot of dedication to materials development, which is essential. As Kenji already implied, the actuator business has been around for a long time, particularly driven by the piezoelectric effect. And what I think you see today is that there's a lot of new things happening in terms of particularly the materials processing. And that's where I'm going to start to discuss a technique which we started to develop about 5 years ago called cold sintering. And as of probably the last year and a half, we have really started to do very low temperature synthesis of ferroelectric materials. And that's what I would give a briefing on. So a number of students and postdocs have worked on this, as well as a number of colleagues. So we started, quite honestly, in secret back in 2014, 2015, and we started with very primitive equipment. You can see an old carver press here in our processing lab. This is where we started. And but since then, we've had a number of colleagues from around the world engage with us, and also the number of publications of people starting to get involved in this has gone up. The National Science Foundation, the Air Force, the Department of Energy, and a number of companies have all partnered with us in terms of starting to push this technology. From the original patent, we now have over 15 licensees, so it's really starting to take off. Now, sintering is one of the oldest technologies that mankind has ever endeavored in. I'm always shocked by, in fact, this is coming from the Ueno Museum in Japan. But there's also been discoveries of 20,000 years of pottery. And most remarkably is this beautiful lady that has been discovered in a late Paleolithic settlement in the Czech Republic, and it's been carbon dated to be 28,000 years old. So the technology of taking powder and applying heat to then densify a material and make a rigid material of various different shapes or functionality is a very old craft for humankind. And if we date it relative to our friends in metals, metal forging has been dated back historically to about 10,000 years. And so for many, many millennia, we have been doing ceramic processing. Of course, in the modern era, we start to get more sophisticated in understanding the surfaces and the colloidal part. But there was often a very, very heavy embracement of driving the kinetic densification with thermal energy. And in a world where we have to be more aware of sustainability, then there is now an opportunity to re-envisage the way that we make and assemble materials. Now, in cold sintering, which is associated with the excess surface energy, and you can have things like coarsening and also the development of new interfaces, the grain boundary interfaces. So the new interfacial energy changes, and that drives densification, and it always competes with the coarsening process. But cold sintering offers a substantial change in that sintering temperature to melting temperature, and it's below 0.2, often below 0.2, as we will show during this presentation. And so this is a 10x change, and it offers an enormously new perspective in terms of how we think and do things. So this is very much in the infancy of a new opportunity for material science, where we will show that you can integrate many different types of materials and try and develop their functionality at these low temperatures. So, as I pointed out, you don't need to have a lot of sophisticated instrumentation. And even an old press with actually a heating jacket was where we really started. And you're applying a uniaxial pressure somewhere between 70 megapascals to 500 megapascals, easily done in a material where you may normally do your lamination, say in tape casting processes. And we've looked at how to scale. We started with normal press dies where you're making centimeters type size samples, to now really quite large areas where you're looking at like 3 inches to 5 inches in terms of the area of a sintered body. So it's fairly easy, and it's a fast process as well. You're taking materials that may have taken hours to sinter, and in 20 minutes you can sinter. I will show you this in a while. The low energy consumption and the sustainability aspect with CO2 emission is important. You're now at temperatures where you can sinter easily ceramic, polymer, and metal together in the same formation to integrate new types of composites and devices. You can work with metastable materials, materials that previously, once you went to another temperature, would transform to a new polymorph, a new structure. And so now you can preserve low temperature phases. You can develop unique combinations of properties in this development of composites. With a polymer and the grain boundaries, you have a chance for re-envisaging what the circular economy would be for hard materials. And of course, without a doubt, there's a lot of new science that now has to be addressed in terms of the sintering process. You can see over here, what we'll talk about in a few minutes, the barium titanate is very low temperature compared to all these other fancy techniques like flash sintering and microwave sintering, hot pressing, etc. So essentially what is happening is we use a transient phase that's going to aid the transport. So it's all about a surface chemistry and a surface additive that, let's say, for example, let's just take water, for example, or acetic acid in the case of zinc oxide, which is the case here. So you use basically an aqueous acetic acid mixture. This is zinc oxide. You then rapidly heat the material, say 15 degrees a minute. You then have surface, very, very small amounts of liquid phase, less than 5%. And then it drives a dissolution process. And then because the system is open, so it's different from the hydrothermal process because it's an open system. So you exploit non-equilibrium thermodynamics. And that will then take a solute into that surface liquid. And then with the evaporation process drives a supersaturation. And then that supersaturation will then drive not only the transport of matter from the contact points, but it will also reprecipitate. And that then gives rise to these high dense zinc oxides, for example. And so there's a lot of details, which I don't have time to get into, which is all about these interactions of the molecular species at a surface. But techniques like reactive force field is developing a lot of insight into how they go. But on a macroscopic level, you can see the sintering process scales with the traditional scaling laws of sintering coarsening, and the activation energies, though, are orders of magnitude lower than what you would expect, right? So the activation energies are severely reduced. So the parameters are the application of pressure, the time, the temperature, no surprises there in terms of sintering. The real difference is really the chemical activity of that sintering aid that then interacts in a non-equilibrium manner to then drive the densification process. So we can track all the densification processes, such as here. We've got a system here where you're monitoring the dilatometer, you've got heat controllers, you've got a system that can have an isobaric pressure applied to the system. And you can see here, 15 degrees a minute, peak temperature of 150 degrees for zinc oxide, typically sintered around 1,000 degrees. And within 30 minutes, you are finished your densification, and within 10 minutes, you are dense and then developing the microstructure. So you're dense by here, 10 minutes, and by here, 30 minutes, you're coarsening the grain structure, and you're looking at this evolution of the microstructure in really unprecedented rates and ways of controlling the microstructure. So I said that it's all about the chemistry. And so here is water versus the acetic acid, 2 mole per cent. Here you can see the densification. So you can see the strength of that acid and how it controls the solute uptake and the dissolution process is critical. But for me, this is just the A to A pathway where you have a transient intermediate phase. We've also seen other ways in which the pathway can exist, where you can go and take a material in a state A to then B. So for example, silica. We've worked with sodium hydroxide, and that's driven a material which then densifies first the silica, and then through the repolymerization of the modifier of sodium, then actually precipitates out a crystallization, which then gives a quartz glass ceramic, all within a 2-hour hold. Or you can have a situation where you can have two mixtures of two precursor materials, and you can form a third material, which is then of stoichiometric ratio to A and B. So let's just look at that as an example of where that third route can be used for particularly electroceramics. So here you've got goethite, zinc hydroxide in a 1:2 matrix, a stoichiometric ratio, and it can form then the spinel zinc ferrite. And here you can see the microstructure for that zinc ferrite. You can also work with, say, a barium titanate powder. You can use a precursor like a hydrated strontium hydroxide, and then you can dope the grain boundaries. We will talk about this type of technique later. So there's a lot of different pathways with understanding different types of chemistry that open up at really low temperatures. And as you can see, with equilibrated grain boundaries. So just to take a step back, we think that at these super low temperatures, you now can integrate many different types of materials. We've integrated gels in the case of battery materials, semiconductors, polymers, ceramics, metals, have all been sintered and co-sintered together in this case. And actually, in the nature of the first session of this conference, we believe that biomaterials can also be integrated with inorganic materials. So I'm just going to take one of these examples, the ceramics and the polymers, where we're putting now a nanoscale polymer grain boundary into the microstructure. And we've demonstrated many different types of, say, thermoplastics, but also thermosets. So you can do in situ polymerization, or you can do a melt crystallization process with these types of fillers. And we're dealing here now with 1 to 5 volume% of polymer, right? So very, very low levels of polymer within these materials. So for example, in a dielectric material, which is of interest for high frequency applications, sodium molybdate, we have been able to put in materials like this polyethyl arim, and you can see here now the grain boundary phase of that Ultem. Ultem is the trade name. And you can see in the triple points, you've got the PEI, and each of these grain boundaries then has a nanometer scale polymer that then in turn changes the breakdown strength to much higher levels as the Weibold statistics of the breakdown strength with this polymer in the grain boundary. You can also put in other types of materials with the polymer or without the polymer. Here are some examples of 2D materials. So here, for example, is a max phase, a Maxine phase, and you can see how with very thin nano 2D materials, how the high strain that they can tolerate can then conform around the respective grain boundaries. You can also take, say, buckyballs and put buckyballs into grain boundaries. And so very, very different ways of controlling grain boundary structure and also the overall material properties. You can make multi-layers with these systems. Here's an example of a anode, electrolyte, and cathode in an all-solid state battery. You can take the tape casting technology and modify it to be able to add polymers with the binder polymer and also the ceramic. So here you need to work with different types of binder systems. So in our case, a polypropylene carbonate, and you can then get the binder out at very low temperatures, around 150, leaving more thermally stable polymers still in the system to then put them into the grain boundaries, like the PEI around the zinc oxide, to then make multi-layer thyristors, for example, or multi-layer ceramic capacitors. So, and in that case, how do you get the liquid phase in? Well, in those cases, we then evaporate it in. You put it in by vapor. So after the binder burnout process, you're evaporating in the active phase that's going to drive the sintering process at these very low temperatures under a uniaxial press at these temperatures of 120 to 130. So how about ferroelectrics? Well, we started working on ferroelectrics almost immediately after discovering this phenomena. And where we started originally was with barium titanate, of course. And to tell you the truth, it was somewhat disappointing. We were able to densify the material 180 degrees within 350 degrees, but there was a lot of problems with the grain boundary phases. A lot of carbonate phases were forming, and then diluting in series the grain boundary mixing. And that dominated the electrical response, the capacitive electrical response, because of the serial nature of the grain boundary of having a glass carbonate phase. And that gave rise to fairly poor dielectric properties, not that exciting. So in this particular case, we realized that we had to decompose and remove this phase. So the first approach was to apply a post-annealing approach to then recrystallize these amorphous phases. It then cleaned up the microstructures, cleaned up the grain boundaries, and then you saw properties in terms of dielectric properties, which are much more familiar to people doing conventional firing of barium titanate. So there was advantages in that, but at the same time, it was somewhat disappointing compared to what we were seeing in other materials. As I said, the breakthrough in the ferroelectrics and doing it in a single step below 300 degrees is less than probably 18 months old. So we published last year, right at the beginning of the year. And here you can see some examples of some very small grain structures, 70 nanometers, 170 nanometer grain size. You can see this was all done in a single step, sintering with sodium hydroxide, potassium hydroxide at 300 degrees. And you can see here some of the dielectric properties showing a functionality which is determined by the grain size. You can see a quite nice hysteresis loop for a nanomaterial grain structure. And actually, if you track in detail where the transitions are, it's also consistent with having size effects with the grain size being this small. You can see that the densification process, so here you can see the linear shrinkage, and you can see that we're sintering within an hour of the barium titanate. You can see the coarsening of the powders. You can see that we're vastly different from before. And you can see that we are almost we are translucent and approaching transparency. And we can use a multitude of powders. Here's a larger powder, the Sakai powder BTO4, which is a 0.4 micrometer starting powder, and you can catch very nice dielectric. So that was a year ago. Within this year, Taka Sada, who's a visiting scientist from Kirishiro, worked with us, and he started using solid forms of this material, which had water bound to the molecular structure of that hydrate. And he found that there was critical levels of the dehydration that would then activate the most effective densification. So there's many things that we don't understand, but in this particular case, the bottom line is he's able now to sinter between 150 degrees to 200 degrees, which is a 50% reduction of what we had over a year ago. And it's that type of technology that allows you to do solid solution, because you can then look within that family of material and dope barium titanate with strontium, for example. You can also add polymers now to barium titanate, but at very, very small volume fractions. So here you can see we're looking between 0 to 15 volume percent of polymer. And this is the type of microstructure. You can see it's sintering, and there's a nanoscale barium titanate, sorry, a nanoscale polymer within the grain boundaries. It has profound effects on the dielectric behavior. In fact, it basically creates a permittivity of 1,000 with almost a temperature invariance. It is fundamentally changing the nature of the material through size effect phenomena. And so this is incredibly exciting. You can see that the behavior for very low volume fractions of polymer, that goes from a Curie-Weiss behavior to then a diffuse phase transformation, just with a nanoscale polymer in the grain boundary. Here you can see some of that polymer in the grain boundaries. You can see the types of microstructure. And there's also, driving some of the size effects, small precipitates of barium titanate, which is in combination with this polymer. And so you're getting now diffuse phase transformations because of the size effect of these secondary precipitation effects, as well as the densification process. So I want to get to the piezo area. So we're also looking at piezoelectric materials. Here's some of the work that we've published on PZT. Just like the early days of barium titanate, we've had to use a secondary heat treatment to then really obtain the right type of dielectric properties. So this problem is not solved yet to my satisfaction, but to show you where we are at the moment, we're using lead acetate and nitrates to then be able to densify those materials. Work we're doing in collaboration with Dr. McKinstry's group. So we've already made some bimorph structures. Here's a copper. Here's some thick layers of PZT on those systems. And here you can see some of the high field switching behavior. And so in this particular case, we're tape casting with these additives. We're doing the binder burnout. We're then adding the steam to then activate the process. And then we're basically then applying the pressing process around 300 degrees, 180 minutes. And then we're doing this post-annealing to then develop the microstructures to the point that gives us the high piezoelectric activity. Similar story in the case of lead-free materials. So here you can see the densification there. You can see the push of a K and N material. This is all unpublished work. You can see this is where the typical materials are. This is where we are with the cold sintering. You can see the densification is occurring within minutes with the K and N system, and here is some of the microstructure. The disappointment is in the defect chemistry of the system. You can see here with this K and N, we've got incredibly pinched loops, although we're able to apply extremely high fields. So we've pushed these materials in bulk pellets out to about 100 kV a centimeter. So the problem is not resistivity, it is the intrinsic pinning of defects. And so here the disappointment is, you know, we should be seeing at least a factor of 5 more defect-free on this material. That inability to switch the domain structures is reflected in the Rayleigh analysis and the alpha coefficient. So the intrinsic part is the same. It's basically, the intrinsic part is equivalent to what you would normally see with the rate relative permittivity. It's in the nonlinear effects that you have a very, very strong pinning, and that alpha coefficient is sometimes 15 times lower than the conventionally sintered K and N. So we start to dope the systems with more traditional ways of modifying the PZT, the lithium tantalate, and you can see here the microstructure improves. The low field permittivity, as I said before, is not a problem, but you can see what happens in the heating up to catch the Curie-Weiss behavior. At 500 degrees, there is an irreversible change because of some changes in the crystallinity of the system, which you also see over here. The Curie-Weiss behavior is standard. And with that heat treatment, you then start to see more better looking hysteresis behavior. Although the D free coefficients are still got to be improved by at least another factor of 2 to 3. But it shows you in this very early days that we need a heat treatment. The other aspect that this needs is scaling. So you can see us messing around at the early TRL levels of this technology, but we need to be able to then make this into a continuous process. All large batch processes, but desirably large continuous processes, and we're working towards that. You can see here that at least within a batch process, we're printing on foils with quite large areas. You can see here large plats of zinc oxide, for example, and also printing on polymers with the dielectric materials and the electrodes. So to give us time for questions, sorry I went quite fast, but this will be recorded so people can go back if they're interested. The most important thing, I think, is a platform for integration of soft materials and hard materials with multiple functionality. I think just as it's taken us about 4 years to improve where we were with barium titanate, and we're now starting the PZT and the piezoelectrics, there will be people come along after this work that will find the magic chemistry to then be able to do this at low temperatures in one step. At the moment, the piezo properties are somewhat limited by defects and pinning of the domain switching. But already, I would say the densification part is coming together and there are real opportunities there. So it's a technique that is continuously surprising us. We've started to classify the different chemical pathways of which can be used. And so it really opens up a whole new world of how to process materials and combine them for functionality. And I think the actuator community has some real advantages here if we can then combine, let's say, shape memory alloy materials with piezo materials and polymers, and maybe even living materials at some point. So thank you very much indeed.
Thank you very much, Clive. I don't find any Q&A column, so I would like to start the simplest question. You mentioned the cold sintering process. What is the practical, the process? Are you using a cold pressing and increasing slightly temperature, or without putting any pressure? You need a pressure.
You need the pressure. The whole process is linked to something called pressure-assisted creep, which is known to the geologists for forming sedimentous rock. And so when you apply that pressure, the contact point between two particles with the appropriate driving force for dissolution, then enables the kinetics to really be pushed to much lower temperatures. The lowest pressure that we've applied is 30 megapascals. The highest pressures, well, we don't really worry too much about 500 megapascals and above. So we try and keep it as low as possible to ultimately scale the sizes. And so 30 megapascals is very similar to where polymer laminate processing goes on.
So if we have a regular cold pressing to shaping the ceramic, that pressure equipment is enough. Just increasing slightly, like a 200 degrees C, using some heat.
With the appropriate liquid phase in, yeah. If you don't have that liquid phase in, then nothing happens, nothing densifies. It just has a green body. But so it's a combination of that liquid phase, the pressure, and temperature.
Okay, still I do not find that other person's question. How about the mechanical strength? You mentioned the highest density seems to be 90%, relatively high. But have you checked the fragility, mechanical fragility, or this, strength?
Yeah, so there has been a little bit of work done on mechanical strength. So the highest densities we've got is 99%, and a lot depends upon your strategy here in terms of removing completely some of the transient phases. So in the case of zinc oxide, there's often a small residual zinc oxide. So if you work at 150, there's a zinc acetate at the boundary. That can weaken the mechanical properties compared to the traditional sintering by, 33%. But if you take it to a higher temperature, then they start to converge. The other thing that you can do in terms of strength is that you can integrate fibers easily, carbon fibers, other things into it. So there's ways of dealing with strength. If you say put a polymer in the grain boundary, you still also want to have strength. You can then design your composite to really basically be able to accommodate weaknesses and strengths in a material.
Other question? Isaku or Jongho? No? So I have one Q&A. So this is the Noran Tolosa. Good day. Is it possible to apply vacuum or negative pressure in cold sintering process?
Well, we need to have the high pressure at the contact points. But I do think that to accelerate, in fact, we are experimenting, to tell you the truth, we're experimenting with fluctuations in pressure. And I could see that if there is a need to get rid of that transient phase faster, then having vacuum would be one way to be able to improve that. So we're looking at dynamics of applying pressure. I see no reason that can't be coupled with maybe ways of accelerating the evaporation process where required. But the process is somewhat sophisticated already. But I think the pressure question is only really opening up at the moment.
At least vacuum is fine.
Yeah, in fact, for a lot of the battery work that we do that also in argon atmospheres as well. So I see no problem with them also working in vacuum.
Clive, you also mentioned some polymer embedded during the CSP process. Is this polymer still remain after the cold pressing?
Yes.
Or
yes.
just disappearing?
It depends on the polymer, but we designed the polymer to be in the grain boundary, a nanometer thick, and the logic behind that for a lot of the applications is that we can choke with that because it's much more resistive, a lower permittivity. It can really change the nature of the local field. So for capacitors, for example, it gives you a way of controlling degradation. It gives you ways of controlling resistivity. And it also gives you a way of dealing with the nonlinearity of the ferroelectric phenomena, for example.
Okay. Any other questions? If no question,
can I ask a question? So yeah, so I have a question about the mechanical strength and the fracture toughness of the cold sintered ceramics. Because usually the high temperature sintering, the mechanical strength of the ceramics is relatively high. So what is the fracture toughness of the mechanical strength, especially against a shock or some of the mechanical impact to the cold sinter?
We have not explored those areas as of yet in any detail, but the initial results on zinc oxide, for example, that was done at a low temperature suggests that it's about 3/4 of the typical zinc oxide. And so there is a small weakness, but I would say that those materials that were measured would not have had the right level of conductivity, because when we looked at conductivity, you have to take it above 300 degrees to completely remove a grain boundary phase. So I don't think a full proper comparison has been made at this moment yet.
Okay, thank you.
Okay, thank you very much. Appreciate for your effort.
Thank you very much.
Clive. Okay, let's move to the next speaker, Professor Kanno, who will talk about the piezo MEMS.
Okay, so first of all, I'd like to express my appreciation to the organized member, especially the Professor Uchino, to inviting me to this conference. So title of my talk is PDT thin films for piezo MEMS from deposition, characterization, and to the application device. My name is Isaku Kanno from Kobe University. So outline of my talk is like this. The first, I briefly introduced piezoelectric MEMS technology. I introduced some of the application devices and their characteristics. Then I'll talk about the deposition of the piezoelectric thin films, especially focusing on the sputtering deposition of the PDT thin films. Then I'll talk about the characterization, measurement method of the piezoelectric coefficient for thin films. So finally, I summarize my talk. Okay. First of all, let's look at the benefit of the piezoelectric material into MEMS by comparison between with capacitors. You know, by decreasing the gap distance of the facing electrode, capacitance easily increased. But all of the capacitor use a high dielectric material inserted into the electrode. It is similar to the MEMS. The sensitivity and attractive force can be improved and increased by decreasing the gap distance in case of the capacitive sensor or the electrostatic actuator. But if we insert the piezoelectric material into the electrode, the actuation performance and sensitivity are drastically improved. because of the excellent energy conversion efficiency of the piezoelectric materials between mechanical domain to the electrical domains. It's independent of the size and the dimension of the piezoelectric materials. So we can realize the functional MEMS devices can be realized even in the very simple microstructure. So that is one of the important features of the piezoelectric material into MEMS. So many of the application devices have been proposed, and some of them have already commercialized gyro sensors, inkjet micropumps, and hard disk actuators. I'll talk about these applications later. But recently, the energy harvesters and the acoustic and ultrasonic devices using piezoelectric materials are the promising candidate for the future commercial applications. And I hear that the optical mirror will be launched in near future, installed into the automobile. So this is the inkjet printer head produced by the Panasonic. So the first commercial product of the piezoelectric PZT thin films installed into the inkjet printer at the beginning of the 2000s. So if we use the piezoelectric thin film, PZT thin films, we can do the microfabrication using a typical MEMS microfabrication process. That is the most important benefit of the piezoelectric material in the form of the thin films. So by using the PZT thin films, high density micropump array can be realized. So it enables very high density and high speed printing installed into this type of industrial printing machine. So recently, Fujifilm launched the advanced printing printer head. Also, it is used for the industrial printer. The concept and the structure is similar to the Panasonic. It launched about 20 years ago, but the difference is the PZT thin films. The Fujifilm used the niobium-doped PZT thin films. The piezoelectric property is about 1.5 times higher than the conventional PZT. So it can be, it enables the low voltage drive, low voltage driving, and it means that improves the reliability and lifetime of the PZT thin films. So another important application is gyro sensors. The almost similar year in the commercialization of the inkjet printer head. The piezo MEMS gyro sensor have been commercialized. The structure is very simple. The typical Chun-Fock structure covered by the PZT thin films. The rotational speed can be measured by by driving the actuation. Is if we apply the driving the actuation, and if we apply the rotational speed, a Coriolis force is generated perpendicular to the axis of the rotation. So we can easily measure the rotational speed. So anyway, the structure is a very simple Chun-Fock structure. Is enough to detect the precise value of the rotational speed. After that, Sumitomo Precision Products, the company name is Silicon Sensing. It's one of the company of the Sumitomo Group. They produced a ring-shaped gyroscope. So ring-shaped gyroscope is also the driving the deformation of the rings. And if we apply the rotational the motion, the perpendicular the force is generated, and this type of the deformation and the Coriolis force can be measured by the sensing electrode. The structure is different, but a very simple structure. And I hear that this the gyro sensor is installed into the Segway. The last the example of the piezoelectric thin film application is the dual stage actuator for hard disk drive. It proposed the Panasonic engineer Kojima-san 2002. The epitaxial PZT thin films attached to the suspension very close to the magnetic head. The very important feature and the required specification is weight, very light, small weight, because the ceramics is too heavy. It disturbs the design of the suspension, and the response is drastically reduced. But you know, the thin film is a very small, lightweight, and it doesn't disturb the design of the total design of the suspension. And another important requirement is linear motion. So in this case, the PDT thin films is epitaxial PDT thin films. So the reason of the epitaxial thin films is not for the large piezoelectric coefficient, but for the linear actuation. So nanoscale positioning is important, required. So the epitaxial PDT thin films is the most suitable material for the dual stage actuators. So 2017, Toshiba installed this type of the thin film, a dual stage actuator. The size of the piezoelectric actuator is much smaller than the first generation, the prototype of the thin film actuator. But anyway, the PZT is epitaxial PZT thin films are used. The epitaxial PZT thin films are grown on the silicon substrate, and after that, the peeling off and transferred onto the this place close to the magnetic head. Anyway, this type of the hard disk drive using a dual stage actuator have already commercialized. These are the very important application of the piezoelectric thin films. So future application is deformable the lens and acoustic application of speaker and microphone is, I think, the promising candidate of the future application of the piezoelectric MEMS. The fabrication process of the piezoelectric MEMS is like this. First, if we determine the application, we have to design the design of the device. And then we have to deposit the piezoelectric thin films. And then we have to evaluate the piezoelectric properties. After that, we can move to the microfabrication and evaluate the total performance of the piezoelectric MEMS device and the feedback. So different things of the typical MEMS device, MEMS process is the deposition of the high quality piezoelectric thin films and the measurement of the piezoelectric coefficient for the thin films. We need to develop this technology to realize the piezo MEMS, the applications. The thin film process and the measurement of the piezoelectric thin films is a very important and fundamental technology of the piezoelectric MEMS. First, we have to choose the suitable piezoelectric materials to fabricate into the thin films. You know, the PZT is the most popular material for the piezoelectric materials. So the PZT thin film is the most popular for even for the piezo MEMS. But scandium doped aluminum nitride is and the KNN have attracted attention not only for the lead-free, but also the piezoelectric property of this material is increasing year and year. So after determining the material, we have to choose a suitable deposition process. Sol-gel, CVD, sputtering, and the PLD is the candidate for the thin film process from the research to the mass production. But among them, Sol-gel and sputtering is very popular, even to the mass production. Because CVD can produce high quality piezoelectric thin films, but the cost of the source material is very expensive. So the piezoelectric MEMS need micrometer thick films is needed. So CVD is the cost is too high. The PLD is very the useful method, but large scale, the uniform thin film deposition is still difficult. So Sol-gel and sputtering the most popular thin film process, and both of them have the use as a commercial production. In case of the Sol-gel process, large-scale deposition is possible by using this type of mass production system. As you can see, the very uniform, the micrometer thick PZT thin films can be produced onto the 8-inch silicon wafer. This technology is used for the fabrication of the piezo MEMS devices such as an inkjet printer and something. And sputtering also is a very useful method. This is Ulbach mass production sputtering machine. You can see the high density PZT thin films can be grown on the silicon substrate, and a very dense columnar structure. You can see the surface structure is very smooth. So it's a very important to do the very fine microfabrication process. So if we look at the sputtering deposition of the PZT, the sputtering condition is almost similar from the research level to the mass production. So we also use the ceramics target of the PZT with MPB composition, but it contains excess lead to compensate the re-evaporation of the lead from the deposited thin films. And the advantage of the sputtering is we can prepare the high quality PZT thin films, not only for the silicon substrate. The MGO is a typical epitaxial substrate. So if we use the MGO substrate, we can get the high quality epitaxial thin films. But right now, is epitaxial platinum can be grown on the silicon substrate. So epitaxial C-axis oriented epitaxial PZT thin films also can be prepared on the silicon substrate. Not only for this substrate, we can prepare the PZT thin films, polycrystalline PZT thin films on the metal or glass. I'll show you the example of the PZT thin films on this material. The typical thickness of the PZT thin film is 2 or 3 micrometer because both for the actuator and the sensor applications, the thickness is very useful to keep the reliability and generating, in case of the actuator, relatively large the force is needed. So the less than 1 micrometer is too thin to produce the sufficient sufficient the force for the actuators. So characteristic feature of the sputtering PZT thin films is we can pick up 3 things. First is the seed layer. If we prepare the good seed layer, we can control the orientation of the PZT thin films. The second one is the self-polarization. Usually sputtering PZT thin films inherently oriented the very stable polarization from the bottom to the top. The last one is excess lead. As I said, the typical sputtering target contains the excess rate, but usually the deposited PDT thin films also contain the excess rate. It shows it leads to the different crystal structure from the solid gel and the ceramics. The seed layer is a very important technique to prepare the PDT high quality, the very crystallized PDT thin films. So if we try to the PDT thin films directly onto the platinum coated substrate, zirconia oxide is preferentially attached on the surface of the platinum. It prevents the growth of the perovskite, the structure. But if we prepare the perovskite layer without zirconium, the PDT thin films with the perovskite phase, can be promoted. So typical seed layer, we use lanthanum dot lead titanate. It's a very useful easy to prepare. And the strontium titanate and the strontium ruthenium oxide also effective to as a seed layer to promote PDT thin films with the perovskite phase. The second, the characteristic of the sputtering PDT thin films is the self-polarization from the bottom of the top. So the detailed mechanism is still unclear, but I think that the oxygen deficient layer, it has a positively charged vacancy, is a trigger to the self-polarization. It's a very useful for especially for the long-term sensor applications. So the Dr. Shepard in the Susan group measure the time dependence of the sputtering PDT thin films. It's a very old paper, but it shows that upward polarized PDT thin films, it is the same as the self-polarization, shows a very stable the piezoelectric coefficient. But if we reverse the polarization direction, the stability of the D31 piezoelectric property is rapidly decreased. So anyway, the self-polarization from the bottom to the top in case of the PDT thin films is very stable. So it is a very good advantage for the sensor applications. So last thing is the excess rate. The sputtering PDT thin films are produced from the ceramics with the excess rate, but usually the prepared deposited PDT thin films also contain the excess rate. But the question is where excess rate exists. So we conducted the Rito belt analysis for the sputtering PDT thin films. The Rito belt analysis need to use powder the samples. So we peeled the PDT thin films on the substrate and grind into the fine powder, and we conducted the synchrotron radiation XRD measurement and did the Rito belt analysis. And the results indicate that about 20% of the lead exists in the B site. So anyway, the PDT thin films produced by sputtering shows a larger the lattice constant than the solid gel PDT and ceramics PDT. So I think this is it is attributed to the existence of the large the lead exists at the B site. So anyway, the existence of the lead in the B site doesn't degrade the piezoelectric property. So it's a very lucky for us But anyway, the crystal structure and sometimes the characteristic of the PZT thin films of the sputtering PZT is different from the sol gel and the ceramics. I think one of the reasons of the excess rate. So Fujifilms is a highly doped niobium PZT they produce, and it's used for the commercialized printer head. But I think it can be realized only by the sputtering. So non-thermal equilibrium process of the sputtering, such as the high speed the bombardment of the sputtered species, is the reason of the different the crystallization process of the sputtering PZT thin films. But anyway, we can control, if we control the sputtering condition, we can realize the new the piezoelectric thin films different from the ceramics and the sol gel PZT thin films. That is a very the interesting the phenomena things for the sputtering piezoelectric thin films. So we can prepare the PZT thin films on the stainless steel foils, and it's the randomly oriented but pyrochlore-free and high-density PZT thin films can be prepared. So we prepare the PZT thin films on the 30 micrometer thick stainless steel foil. And it's very flexible, so we can easily bending, the large bending. So we try to use this type of the PZT foil for the energy harvesting applications. The student bending the PZT coated stainless the sheet, it generates a relatively large voltage, and the output power reaches the 70 microwatt. It can be used to operate some of the sensor and the sensor nodes. We try to use try to operate the just a moment. The Bluetooth low BLE module powered by the flexible PZT thin films. You can see the temperature and the humidity data is transmitted from here to the receiver, and the temperature data is displayed in the screen. So anyway, the very large bending motion can be applied without peeling off and the cracking of the PZT thin films. So the next thing is the PZT thin films. We try to prepare on the glass. So the transparent electrode coated glass we used. Then we prepare the PZT thin films by sputtering. So of course we use a seed layer. So we can get the pyrochlore-free PZT thin films on the glass substrate. So we measure the dielectric and the ferroelectric property using a transparent ITO top electrode. And you can see we cannot identify where is the ITO, but anyway, good dielectric constant and very the typical ferroelectric hysteresis curve we can obtain. So we also measure the piezoelectric property of this type of the transparent piezoelectric thin films, and we confirm the almost same the piezoelectric property with PZT thin films on the metal substrate. Another important technology is the measurement. The precise value of the piezoelectric coefficient is very important to design of the piezo MEMS. So, but the problem is the existence of the substrate. So we cannot use the conventional measurement method for the thin films. So we need to develop the new useful measurement method for the thin films. So several methods have been proposed. The Susan group proposed Weber bending, and Exact use double laser beam method, but it's a very expensive machine. So we propose a very simple cantilever method. Just cut from the silicon wafer and then the clamp to one end of the beam, and we applied the external voltage between top and bottom electrode. So we can get the very precise value of the tip displacement by using the laser Doppler vibrometer, and we can calculate the piezoelectric coefficient. The direct piezoelectric also can be calculated by applying the external force by the external force at the tip of the cantilever. The equation is very simple. Output the charge and the input displacement. These relationships are derived to the precise value of the E31F of the dielectric the piezoelectric coefficient. As I said, the converse piezoelectric effect also can be derived by this type of this simple equation. From the relationship of the tip displacement, output displacement, and the input voltage. So anyway, we measure the polycrystalline and the epitaxial PZT thin films, the piezoelectric coefficient E31F. This case is a direct piezoelectric effect as a function of the input tip displacement. You can see both thin films shows very the constant the piezoelectric coefficient. So here is a converse piezoelectric effect. So the epitaxial PZT thin films shows a constant, but polycrystalline PZT thin films is a nonlinear characteristic. I think this is due to the extrinsic effect. But anyway, by simple measurement of the unimodal cantilever is represent the characteristic feature, the microscale the characteristic can be evaluated by the macroscopic piezo cantilever method. So it's a very useful not only to identify the piezoelectric property, but also how to improve the piezoelectric property for the thin films. So the summary of my talk is a piezoelectric thin films for PZT thin films for the piezo MEMS, inkjet printer head, gyro sensor, and hard disk dual stage actuator have already commercialized. Acoustic optics device and energy harvester is, I think, the promising candidate for the future applications. The sputtering deposition is very unique and different from the solid gel and other depositor piezoelectric thin films. But anyway, we can control the crystal structure, and we can also control the piezoelectric property. The evaluation of the piezoelectric measurement is very important, but the simple cantilever method is very useful not only to get the precise value of the piezoelectric coefficient, but also the intrinsic characteristic of the piezoelectric thin films. So I'd like to thank the collaborator, Professor Uchino, Professor Priya, and Professor Nam, and my collaborator and the funding source, and my student. Thank you very much.
Thank you very much. Any questions from the audience? So I would like to start my question. Third from the last slide, you mentioned the PZT on silicon and on MgO.
Yeah.
And the D constant is not the D, E constant is significantly different. Why silicon is much better than magnesium oxide?
Yes.
PZT. PZT should be the same.
Yes. Yeah, same. But PZT on MgO is epitaxial PZT, and the silicon is polycrystalline. So anyway, a direct piezoelectric effect is a constant, but the converse piezoelectric effect is polycrystalline PZT shows a larger piezoelectric coefficient. and a non-linear effect also observed. I think the PTT on silicon substrate has a tensile stress, but on MGO substrate, epitaxial MGO PTT thin films has a very strong the compressive stress. I think that it's the reason is the compressive stress, the stress difference of the stress states, and I mean the crystal structure, polycrystal, and or epitaxial. Yeah.
I see. Thank you very much. A question came from Nolan Tolosa. Good day, Professor Kanno. Does the performance of PZT on its preparation using a different precursor, such as the for titanium, also matters? So different precursor also matters.
The question is the seed layer. Precursor is
this doesn't mention any. So
yeah, because I'm just trying to ask whether if you use different types of raw materials in preparation of PZT, does it matter if you use different materials or raw materials in preparation of PZT? That's what I'm referring to precursor.
Raw material means the target material or
the material used to prepare PZT.
Mm-hmm. So in case of the sputtering PZT, so we use the ceramics target with the MPP composition, but we added the excess lead oxide. The precursor is actually I have not made the ceramics target by ourselves, so I'm not sure the source material, fabrication of the source material.
Just purchased from some supplier.
Mm-hmm. Yeah, usually we buy the ceramics target from the company, ceramics company. So anyway,
Okay.
Yeah.
Thank you very much.
Yeah.
Thank you. Thank you so much.
Anyhow, it's already time, so we'd like to move to the final speaker. Not the final. Final would be me. So Jongho Ryu, Professor Jongho Ryu, who will talk on the AD aerosol deposition.
Thank you, Professor Uchino. My name is Jongho Ryu. I'm working at the School of Material Science at Yeongnam University, Korea. Today, I'm going to talk about the piezoelectric thick film fabrication by aerosol deposition. Actually, Professor Kanno talked about the kind of thin films by using sputtering mostly, but we are doing similar things, but not sputtering. It's kind of a new technique, which is not the commercialized yet. So aerosol deposition technique can make several kind of piezoelectric materials. I will talk about that techniques today. So as Professor Kanno mentioned that there are so many MEMS devices which is using the piezoelectric thick films and the thin films. He said that the two thin films cannot generate enough power or sometimes low sensitivity in the sensor applications. So it's like if we make some kind of thick materials, the piezoelectric properties are good, but it's a little difficult to make small devices. But thinner material case, we can make the very tiny devices, but piezoelectric properties are not very good compared to the bulk materials. So if we make a kind of a thick films, for example, like 1 micron or 10 micron thick films, we can enlarge a lot of the application areas like very strong the MEMS actuators or very sensitive sensors, such kind of things. So here the problem is like how can we make a thick films rather easily? There are so many kind of thin films or thick film fabrication techniques in the world. So for example, to make thin films like a CBD or chemical solution deposition, it's a kind of sol gel, and CBD sputtering and evaporation, PLD, that technique is very good. We, as Professor Kanno said, this technique can make a very sound films with very good homogeneity, but it's a little tough to make 10 micron thick films. Typically, it's like 1 micron thick or couple of micron thick films is okay. But the thick film side, there are the other techniques like tape castings, screen printings. This is good for the several tens microns, but not good for 1 micron or 10 micron thick films. So here, aerosol deposition can cover from the several 100 nanometer to the sometimes 100 micron thick films rather easily with very high deposition rate. So actually, the aerosol deposition technique is born in the late 1990s, like 1999. So that is born in Japan. So many Japanese groups are still working on that. So most of the works, more than half, had been done by Japanese national labs and industry as well, university. And some are done by Korean, like me. So actually my group at KIMS, before my prior is the affiliation was KIMS, they are actually very intensively working on that. And the other, some universities are also working on the aerosol deposition. And some Chinese research institution and the universities are also working on the aerosol deposition. In US and Germany and Europe, there are not many many research groups are working on the aerosol deposition, but there are some groups are working, especially German groups. There are 3 or 4 now, and US Applied Materials, the company, and also some university and naval research labs are working on the aerosol deposition. This next graph shows the published number of papers. So gradually increasing in these days as well. So yearly like 50 papers or 40 papers are published in the journal. So then what is the aerosol deposition? So it's simply I think you can, let me talk about the machine. The facility itself is very simple. There is a deposition chamber, which is connected with the vacuum pump. And then there is the other chamber, we call it aerosol chamber, which contains the particles. And there is a gas, carrier gas. We can supply the gas. So when you turn on the vacuum pump, that chamber will be evacuated. So in the vacuum level. So then we are turned on the MFC. That means like a gas is flowing through this tube. And this gas meet inside of the aerosol chamber with the powder, then it will be a aerosolized particle suspensions. So inside of this particle, there is no liquid or no binder, just like a particle and gas. Then this particle suspension is flowing through the tube, and inside of that chamber, there is a one nozzle here and the XYZ stage. So we can attach the substrate here and spraying the particles. Typical the particle speed is like a sonic speed, 300 meter per second. That is 1,000 kilometer per hour, like a jet plane speed. So by using the solid state particle without any liquid, then we can make dense ceramic films because of this high kinetic energy of the particles. So we don't use any binder or liquid. So here is the similar phenomena. So bullet impact on a wall, the very rigid concrete walls. The normal bullet speed is like Mach 2 or Mach 3. So you can see here. So bullet is metal. There is a plastic deformation as well as fracturing. So big bullets become like a very small particles. So aerosol deposition is using the similar phenomena. So we are spraying ceramic particles and hit on the ore like a substrate, then particles deformed and fracture to the nano size. So this is the schematic of mechanism. So we are spraying the particles from the nozzle. Nozzle is on top over here. Then particle size is normally 1 to 2 micron size, depending on the material. And speed is 300 meter per second typically. and this is substrate. So when we separate, the particle has a very high kinetic energy, so collision will happen at the substrate. And then the next sprayed particles is hammering to the fractured one. So because of the high kinetic energy, this particle break down into the nano-size small particles, like 1 micron to several nanometer size. So nanometer size particles has very high surface energy compared to the bigger size particles. That means the particles are unstable. They want to stick each other. So that is what we are believing for the densification of the aerosol deposition. And next, the following particles are hammering to the already deposited layers. So densified continuously, and we can get the thick films rather easily at room temperature. So this is one of the movie that I can show you. It's not working. So anyway, let me skip it. So because of that mechanism, so typical microstructure of the aerosol deposition film is like that. So this is titanium oxide films, which we worked on this like 10 years ago when I worked on the photocatalyst. So we are spraying like micron size particles, and then we can get this kind of typical nanostructure, the microstructure. You can see here scale bar is 10 nanometer. So black parts are crystallite. The white areas are highly disordered glass-like phase, like an amorphous phase. So small particles, small grains are dispersed very uniformly inside the amorphous matrix. The size of the crystallite are typically nanometer to the several tens nanometer, which is good for the nanomaterials like a catalyst or some porous nanostructured materials, but not very good for the piezoelectric or ferroelectric materials because it is smaller than critical grain size of the ferroelectricity. So we need to do something like a thermal annealing. So by the way, my team actually spent more than 15 years on the aerosol deposition. We tried to optimize and make the application areas for a long time. So this is one of our approaches. I will summarize what we did during the last 15 years. So since the technique is not commercialized yet, we were trying to commercialize this technique for various applications. So for the commercialization, we need very high, large area deposition with a high depth rate. So for that, we conducted aerodynamic simulation to make a very fast airflow for the high-speed deposition. So we designed the so-called Laval type nozzles, which can make a more than Mach 2 speed of the particles. By designing this one, we can make very uniform the PGT films on the glass or any other substrate. This is one of the example, like a 400 millimeter, which is 40 centimeter by 40 centimeter. That deposition rate was like nearly 1.4 micron per meter. As sputtering is typically 3 micron per hour or 2 micron per hour, which is this speed is much faster than sputtering or other PLD. The deposition of the film speed, the depth rate is really fast, and also you can see here this film is 5.5 micron thick. Of course, because the mechanism of deposition is using high kinetic energy of particles, surface is not very smooth like a sputtered films, although the uniformity itself is not very bad. So when we are making the MEMS devices, sometimes we are polishing, CMP polishing on the surface. It is possible because thickness itself is sometimes we can make a more than 10 micron or 20 microns. This is one of the good example of our machine. So I'm not so tall guy, but I stand in front over here. My height will be around here. So chamber size is a 1.5 meter and length is 2.5 meter. So inside there, 1 meter nozzle is installed. So by using this nozzle, we can easily deposit this kind of large area films, 1 meter by roughly 650 millimeter size. At the time, this one we made like 5 years ago. So that time it was world largest ceramic films by aerosol deposition. So if we put the silicon wafers here, we can deposit more than 50 wafers in one time. And because of the high deposition rate, we can make this kind of films in 10 minutes or 20 minutes. So since that process is a room temperature process, we can use any kind of substrate like polymers or very low temperature, low thermal budget substrate like here, copper foils or nickel metal foils, amorphous films, and ceramics. So this is one of the example of a flexible dielectric. The BGN is a typical dielectric material which has a relatively good dielectric constant even in the amorphous phase. So we sprayed this powder on the copper foil that we got the very similar performance compared to the BGN film on the silicon substrate. So flexibility also is possible, and also dielectric property was not bad. And sometimes we can deposit the films on the plastic substrate, for example, like PET polymer, typical polymer substrate, and we can deposit the ferrite films on top of here, and it is flexible. If we don't bend completely, then it will be okay. Like a not folding, that will be okay. And we spent a couple of years on the flexible energy harvesters, but that time we could not deposit the films to this polymer substrate directly. So what we did was like here, we sprayed the particles on the sapphire, optically transparent, and we got the very dense and thick films. You can see here 7-micron thick films without any pores. And then we transferred the films to the PET polymer substrate by using laser lift-off process. After that, we made the electrode and the passivation layers. Then this is the final device. It's flexible, the energy harvesters. By bending motion, this guy can generate electric voltage, and we can rectify it and save to the capacitor, and we can operate the wireless sensors like Professor Isaku Kanno did. So this is one of the example. By folding the harvesters, this guy is generating like more than 100 volt peak, and then we can save to the supercapacitor and send the power to the wireless sensor that can monitor real-time temperature and environmental conditions. So it is possible to use this one for energy harvesters. Then the other many people are asking us, what about the sensor applications? Some sensors, for example, acoustic emission sensor in this case. So titanium metal substrate, they want to deposit multiple layers. For example, here titanium substrate and strontium titanate for the diffusion barrier, and lanthanum nickel oxide is bottom electrode, and PGT thick films and the top electrode, LNO. So here you can see roughly 10 micron thick films made by aerosol deposition. Not only PGT, but also top and bottom side electrode, and also the bottom diffusion barrier also deposited by the aerosol deposition. That was really challenging at that time, but we successfully made the 4 types of different layers was successfully made by same process. And then this acoustic emission sensitivity also not very bad. It's acceptably good. And then people are asking, the multi-layer has always have problem of delamination because of the thermal shock or continuous driving. So we check these fatigue behaviors at room temperature and the low field and high field. With up to 10 to 9 cycles, there was no significant changes. So reliability itself was not bad. And thermal shock also one of the good issue in the serious issue in the industry. So what we did is minus 30 to the 85 degrees C changing in 30 seconds. So how many cycles films can be survived. So we tried the 30 cycles, like changing the temperature from -30 to the 85 degrees C 30 times, but there was no significant change. So even though we made multi-layers, there was no critical issue in the reliability. Then this technique is good for the thick films actually. Thin film case is not very good because there are so many good thin film deposition techniques. So we are trying to make a thick films by using this one, but the always problem is the residual stress. When we make the thick films, that interfacial residual stress is highly accumulated and sometimes make the cracks or delaminations. So we added a very small amount of polymers to the powder and then spray it together like a composite films. After that, we burn out the polymer polymer powders. Then we can get some stress relaxed the thick films. This is one of the data. So after annealing at 900 degrees C, we got the more than 100 micron. In this case, like 70 micron. The D value here, you can see over 500 picocoulomb per Newton. That powder was a PGT5H, so it's very similar to the bulk ceramic materials, but these thick films on the silicon substrate. So microstructurally, you can see here. So this is 100 micron thick films. Very tiny nano-sized pores are generated to relax the residual stress. That is from this polymer after burnout. So very uniformly, the nano-sized pores can relax the residual stress that can make the film sound. So compared to the typical screen-printed films, pores are much smaller and uniformly dispersed. So reliability viewpoint is much better microstructure compared to the normal screen-printed one. And as a sputtered film, the AD can also control the residual stress level. What we did was we just simply changed the substrate, for example, zirconia, sapphire, and silicon, that each material has a different thermal expansion coefficient. PGT is typically roughly 5 ppm per degree C. So in this side, it's very strong compressive stress can be generated at top side. That means like a C-axis domains can be easily aligned. So we can have a beautiful, relatively good ferroelectric behavior, like high polarization values. And also D value is 2.5 times larger than normal silicon vapor-based thick films. And sapphire is in the between these two guys. So by just simply changing the substrate, we can control the residual stress, and then we can get the higher piezoelectricity from the films. So this is one of the example, like polarization values and the D values are changing with the residual stress. And what we did, this is actually quite a long time ago, like 14 years ago, when I do the AD for the first time. So that time, one of the issue was lead-free piezoelectrics. So typical lead-free material is a potassium sodium niobate. It is a little bit difficult to make a highly dense body at the time. That time it's normally KNN density is 90 to 95%. So you can see here a lot of pores and facet grain boundaries is a little bit difficult to densify. So we sprayed the powder at room temperature, and we got the 70 micron thick films and without any visible pores. That after annealing at 700 or 800 degrees C, you can see very beautiful the ferroelectric hysteresis. And even we could measure the piezoelectric coefficient. D33 was roughly 50 picometer per volt, which is not very good. But at the time, no one succeeded make the lead-free KNN thick films. And we measured the D value for the first time. After that, we were trying to make a more thick films, KNN, BT, barium titanate. That time it was 20 micron thick films, very highly dense films. And then D value become like 100 picocoulomb per Newton. So this film is transferred to the the University of Southern California, Jung's group. They are interested in making some kind of medical transducers. So we provided our films to them, and they made this kind of needle type transducer, and they made the device and characterized. Frankly, I do not know very well about the performance of this one, but they said at 200 megahertz, which is good for skin diagnosis or the retina diagnosis, it's good for such kind of applications. So for the other MEMS devices, some people are asking, AD can do the patterning for the MEMS devices. So we did by using photorisography and the lift-off process. This is one of the example. After that, we optimized the process. For example, 6-inch wafers, and we did SiO2 layers, and then SU8 patterns, and then deposit the films on these areas. And lift off and annealed and the DLI, then we can have this kind of membrane devices. This is real devices. So 6-inch wafers, we made the PMOT devices with more than 2,000 elements or patterns. This is a magnified view. So you can see here, so PG thick films is 11 micron, and very highly dense. Of course, the quality itself is lower than the sputtered films, but thick films has some meaning. So we made the beautiful PMOT devices, and we tested the vibration and acoustic powers as well. This is one example. So this is LDV measurement. We got the 1.5 micron, the displacement at the 5 volt peak to peak. Of course, it depends on the size of a PMOT device. This is UC Berkeley data. They made the beautiful PMOT device by using the sol gel films that they are applying 10 volt peak to peak, but normally it's like 1 micrometer displacement. This is much better than that. That is due to the thickness of the films, we believe. And the coupling coefficient also 2.5 roughly, which is very similar to the sol gel films. And we were trying to make some kind of composite. Actually, my main background is a magnetic material and the piezoelectric material, mixing together and making composite. So we synthesize the PGT-based material and the ferrite materials mixture. We sprayed this kind of particulate composite is possible, and also we made a lot of the layer structures, as you see in the acoustic emission sensor slide. And sometimes people are asking porous materials. So this one is one of the example. We have a similar method can make the porous body. So we mix together titanium oxide and the 3-calcium phosphate. This is a water soluble that we mix together and spray. Then the films will be kind of a composite. After reaching out the 3-calcium phosphate, then it'll be like a porous. So we use this one for photocatalyst. Of course, this one cannot be used for actuators, but the sensor viewpoint, it can be used for the gas sensors. And not only functional materials, this aerosol deposition can deposit a very hard material like a silicon carbide and titanium nitride. This is not our data. This is from the AIST Japan. So they can make a beautiful hard materials like more than several tens micron thick films by using this one. Probably this one can be used for ultrasonic motors like a friction resistance materials. So AD has a lot of advantages. We can make a relatively dense films, and depth rate is very good, and all process are room temperature, and adhesion strength is good, and nanostructured material, we can obtain it. That is problem for piezoelectricity or ferroelectricity. We need some kind of thermal treatment. So recently we are working on the laser annealing, work with Shashank Priya, Penn State now. So we are deposit the films on the metal substrate, amorphous metal. So amorphous metal is a real amorphous, so we cannot anneal that once. So sometimes we need to anneal locally, just PGT only. How can we do that? If we anneal this one in the normal furnace, the material will be crystallized. We cannot use this material anymore. So we adapted the laser light on the surface of films. So this is a simulation when we irradiate the 560 nanometer wavelength lasers to the surface of PGT films on the matte glass. Then you can see here, roughly 600 Kelvin heat generation, heat lights can be obtained by using simple laser in 1 second, and no damage to the substrate side. So we adapted that one to the real system. This is film, 4-micron PGT thick films. We laser scan here and here. So beautifully annealed, you can see here. As that films are quite broad peaks, that means rather small grains or amorphous phase, peaks are become sharper. And from the TM microstructure, substrate side didn't change anything that before and after laser annealing, but the PGT size, you can see here clear ring patterns. That means like more crystallization happened. So selectively, we anneal the PGT films without damaging this substrate side. So we check the ferroelectricity and the magnetic properties. So you can see here, this is normal furnace annealed films, and this is laser annealed films. A little bit worse than this guy, but reasonably good, the ferroelectricity and also dielectric properties. And the magnetoelectric properties, that material itself is a magnetic and the piezoelectric combined together. So when you apply the magnetic field, then we can get the electric signal. That is magnetoelectric property. So theoretically, based on this equation, we can get this kind of a tendency. From our laser annealed film case, it's nearly same as theoretically calculated values. That means like a performance of a piezoelectric film is not degraded at all, and also McLaughl's magnetic properties still keeps the original state. So this work has been published in these 2 journals recently. So let me close my talk with this conclusion. So we can make a lot of functional materials, but today I just mentioned about the mostly piezoelectrics. So AD can make thick films. It's good for thick films, not good for thin films. And the deposition rate itself is very high, and the room temperature process. Large area is also possible. And there is many parameters to control the piezoelectricities, like thicknesses and dopings and multi-layers. Lead free is also possible. Magnetoelectric is also possible. And for the special thermal treatment, laser annealing is also possible in this case. So we can use this one for various kind of piezoelectric applications, we believe. So actually, this whole story is published in the Actuator journal recently, like two months ago. So you can read this one, then you can figure out what we are doing and what the other Japanese peoples are doing. For example, Jun Akedo is from AIST, inventor of this process. So his story is also written in this paper. Okay, thank you very much for your kind attention.
Thank you very much. Any questions? So Jongho, I will start a simple question. AD process, does temperature also increase during the impact or just a mechanical crashing? How high temperature increase do you expect?
Actually, we are trying to measure the temperature, but there was no the apparent temperature changes. But based on the Jun Akedo's simulation, there is a several 100 Kelvin, like a 200 or 300 Kelvin temperature rise happens in picosecond or nanosecond range. Mm-hmm. It's a very short time, just like small temperature rises, but we don't believe that is really effective for the densification. It's just like a very short time flash.
So you believe basically mechanochemical reaction to make some stack?
We believe so.
Okay.
there is no strong chemical reactions normally, but we didn't very carefully explore them.
Okay.
So maybe not.
But the particle, I mean, small grain and small grain must be very adhesion some force is required.
Yes. In that case, there will be some kind of small chemical reactions.
Okay. So the PZT original in situ, this powder size is much smaller than 1 micrometer. Therefore, you definitely require the annealing process. Is my understanding correct?
You mean low powder?
No,
low powder is normally
crushing,
1 micron.
The raw films already made.
After crushing is normally the particle size after crushing is several nanometers or 10 nanometers, very small size. So that's why we did the kind of.
You need annealing.
Yes.
How low temperature annealing is basically required to get reasonable PZT performance?
Very recent our paper, our result, like 500 degrees C is necessary, minimum. But to get the good performance, 700 or 800 degrees C is necessary.
Okay. The last question is the density. As long as I see your cross-sectional view, that seems to be 98 or 99% really dense. Is it really correct?
Yes, when we measure the density by using Archimedes method or the other techniques, the density is normally 98% or higher. But sometimes, of course, less than 95. But normally, we are saying over 95%, typically.
Okay, thank you. Any questions from the audience? No more question? Okay, thank you very much again.
Thank you.
I will start my. Okay, I will present the high power piezoelectric materials. Basically, this is one of our regular presentation. Therefore, this is the 10-minute shortest, the summary. So I didn't change any, the titles. So started from a high power piezoelectric background and loss phenomenology and high power characterization system, and also high power performance in PZT, and as well as the lead-free piezoelectric materials. And finally, a short summary and future. Because of this very short, the lectures, you may need some references. So I presented the 5 textbooks, which is regularly used in the Penn State University. The ferroelectric device, this is for the materials, class, and the micromechatronics. This is basically the drive control mechanism for the EE and mechanical engineering. And computer simulation is also taught, okay? And this is probably the best for the all audience. Ferroelectric devices and the piezoelectric actuators. This is instructor manual. This installed 250 question and answer beautifully. Therefore, you can use it for your class. And high power piezoelectric loss and loss mechanisms. This has been published a couple of months ago. Therefore, this will be really the good, the references for your purpose, okay? Why high powers? So piezoelectric materials, my contribution is relatively high for the piezoelectric transformer for the Apple computers, laptop, backlight inverter, a little older age, like a liquid crystal display period. So this is basically the, how many, how many million, 10 million, 20 million production has been already made, okay? And the next one is a metal tube ultrasonic motor. This is one of the smallest motor. You have probably seen and in collaboration with Samsung, the electromechanics, we developed the metal tube ultrasonic motor. Was the first, the smartphone camera module. Anyhow, during this period, this is just Apple computers, the simulation. So the piezoelectric devices, when we shrink, the heat generation is a significant problem. So basically miniaturization, we need to increase the power density per unit cubic, the centimeter, okay? How much energy can be really handled. This is most important. When I started this area, only 3 or 4 watts, that's the maximum. So we need to use a huge bulk of ceramics. Nowadays, roughly 10 times higher power energy density, 30 watts per cubic centimeter is utilized. Therefore, even the laptop computers, only 1 cubic centimeter is sufficient to drive or some adapter, transformer application. That's the current situation. So I would like to summarize in this 35 years, the long period research in 10 minutes, okay? So high power loss phenomenology. Basically, when we measure the stress strain, we can measure the elastic, the loss from the hysteresis. The polarization electric field dielectric loss can be observed. And the strain, stress, or the polarization electric field relation, this hysteresis will provide a piezoelectrics. Not many people are integrating in the piezoelectrics, but I will explain. Piezo is the largest energy, the loss contribution in the piezoelectric materials, elastic, dielectric, piezoelectrics. So IEEE standard, unfortunately, installed only the elastic loss itself. Therefore, anti-resonance, resonance, mechanical quality factor is always the same, okay? So far it's fine, but the miniaturization, we need to clarify the piezoelectric loss. Basically, PZT materials, usually anti-resonance is much higher efficiency than the resonance drive. Therefore, we need to really clarify the piezoelectric loss. So already more than 10 years ago, one of my students developed the mechanical quality factor resonance and anti-resonance. Both are shown here. You can easily find that anti-resonance is much sharper. Using this, the difference anti-resonance, resonance, and anti-resonance mechanical quality factor, we can determine the 3 losses. Started from the resonance, okay? We can develop, we can calculate directly elastic loss, and the dielectric loss is obtained from the off-resonance. Therefore, from the anti-resonance mechanical quality factor, we can derive the piezoelectric loss automatically, okay? And in PZT materials, lead-free is opposite, but the PZT materials, anti-resonance is always sharper. That means the piezoelectric loss contribution is much larger than the dielectric or elastic losses. So the heat generation is supposed to at anti-resonance due to a large piezoelectric loss. So heat generation is suppressed at the anti-resonance. So I will show you the practical, the experimental result, okay? As I already told you, this is the most familiar IEEE standard equivalent circuit. In this case, R1 itself, that means elastic loss is installed. QA is equal to QB. So this creates a big discrepancy from the practical experiment, okay? A discrepancy from the experiment, PZT, usually QB is much larger. To the contrary, interestingly, and the lead-free materials, the QA is sharper than the QB, okay? That happens. Therefore, piezoelectric loss contribution as I already mentioned, the QA, QB difference comes from the piezoelectric loss, okay? So this is our current setup. The key point is a driving circuit. To the typical piezoelectric devices at resonance, mechanical quality factor, high mechanical quality factor Q means like 1000. Therefore, current is really large. Current is required, 10 ampere. So when I was a vice president at NF Corporation in Japan, we developed this NF the amplifier. So 300 volt, 10 ampere is directly utilized. Okay, adjuvant impedance analyzes this doesn't have this kind of effect. So our measurement is vibration constant method. That means, as you can see here, okay, this vibration is maintained. So output mechanical energy is constant. And by changing a current and voltage alternatively, okay, both are changing automatically and measuring the impedance, okay? So thermal camera also creates some images. So stored mechanical energy constant, this is our standard measuring system. So how about the high power PZT result? The mechanical, the Q sub M, QA resonance and anti-resonance QB are plotted. You can easily find that the QB is much higher. And both cases, just around the 0.1, 0.2, meter per second vibration velocity, the dramatical temperature rise happen. So we set the 20 degrees C temperature rise from a room temperature. That corresponds to the maximum vibration velocity. This is the limitation of the PZT materials usage. So when I started, as I told you, 0.3 meter per second, that corresponds to a couple of watts per cubic centimeter. But we developed 0.8 to 0.7 meter per second. So that means 4 times higher energy density has been already achieved. Therefore, we largely distributed the piezo transformers accordingly. So if I show you the resonance and anti-resonance, both situations, temperature profile, and resonance create 100 degrees C temperature rise under the same vibration mechanical output levels, but the B-type anti-resonance, we can generate just only 60 degrees. So that you can suppress the temperature, the temperature or heat generation and increasing the vibration velocity, okay? So QB is better efficiency. So how about the lead-free materials? So lead-free materials, Dr. Grudal already, they reported lots of these results, but compared with the PZT degradation with a vibration velocity increase is significant. Therefore, we cannot use the high vibration levels because temperature rise is so significant. To the contrary, the lead-free materials, temperature increase is really stabilized. Q sub M drop is really stabilized, so that we can, we can get the 0.8 or 0.9 meter per second, the vibration levels. So the power density in NKN, sodium potassium niobate based, is higher than the typical hard PZT. That's the current result. So scientifically, it's interesting. QB is higher than the QA for the PZT, and the QB is almost equal, or sometimes QA is higher for the lead-free materials. So we are now trying to clarify the microscopic origin of this loss mechanisms. So final summary will be made. So in 1980s and the 90s, we worked lots on the real part. So high strain materials may be important. Therefore, we worked lots on these materials. But actually, we can develop the 1% strain levels in ceramic. But unfortunately, the self-cracking happens if we develop the 1%. Therefore, we cannot really apply much higher than the 0.2% of the strength, taking into account the mass production. Therefore, we don't need to develop a so high strain materials anymore. Rather than that, in the 21st century, from real to imaginary, temperature rise is significant. So how we can suppress the temperature rise? That is the futuristic research topic, and from high strain to low temperature rise. This is the current, the research trend in the 21st century, correlating with the sustainability areas. Thank you very much. Any questions? No questions? In that case, it's already time, so I would like to pass the final remark to the Elena.
Thank you, Kenji. So yeah, I guess we will end the webinar or live session here. But before we go, I'd like to thank once again, our session chair, Professor Uchino, and our three speakers, Professor Kanno, Professor Ryo, and Professor Randall. And well, for you participants, thank you also for joining us today. And you should, if you are able to attend, please remember to register to upcoming live sessions of this conference that will be on Thursday and Friday. I'm not sure. I don't know if, well, we have some messages in the chat, and well, I think it's here. Bye-bye, take care, and hope you enjoyed it.
Clive, Isaku, and Jongho, thank you very much. We'd like to see you in face next time.
I'll back to home and sleep.
Okay.
Yeah. Thank you.
See you.